Okay, hello everyone. I'm Ruifeng from Arm, and in this session I will talk about a feature on the platform on the architecture that is called SVE, and my experience of integrating this feature into DPDK. First, what is SVE? So SVE, it is short for Scalable Vector Extension. It's an addition to the architecture instruction set. So as you can see, it is for vector processing. So vector processing is not a new thing in DPDK project, as you can find a lot of code in libraries, in PMDs, that is doing vector processing. For SVE, it is different from the traditional vector. So here you can see from the diagram, this extension supports vector lengths that from 128-bit width to maximum of 4096-bit width, and in the granular of 128. So yeah, the vector bit width, it can be different for different hardware. Yeah. Okay. Yeah. So the vector coding in DPDK. Yeah. As you know, DPDK processes packets in bulk, so it takes in a bulk of packets and do the processing at the same time. So it accelerates the operation of data processing. So yeah, we just talked about SVE and what's the difference from the traditional vector. You know, in the traditional, the vector length, it could be fixed. For example, on ARM platform, the Neo extension, it is 128 in bit width. And in some other architectures and in more advanced generations, the vector bit width can be wider to 256 or 512. Yeah, so that may create some problem for programmers how we program to use the vector engines. As you know, we process the same data, but the hardware has different vector lengths. How we program for different hardwares. So here, SVE, it provides ability of compile once and run everywhere. That means the same code, after compilation, then the binary can run on different on hardware that with different vector length. And yeah, I will talk more about it later. And also, SVE is scalable vector extension. So what is the scalable? I think it includes two things: functional scalability and performance scalability. And from functional perspective, it means the same program generates the same result on different hardware, regardless of the vector length on this hardware. And the performance-wise, the portability means the performance of the program will scale when it moves from smaller vector length to bigger vector length, and the performance skill should be proportional to vector length. Okay, about how the program adapts to different hardwares. I will not talk about the hardware implementation that enables this, because that's a thing of hardware guys. So I will talk about from software aspect. From software, there's a concept called VLA, vector length agnostic programming. So that means when you program for the SVE engine, you don't need to know the exact hardware vector length. So that makes life easy. And what makes this possible? There's a concept called predicate. So typically in vector processing, you need two source registers, and after some processing, the result is stored in some destination register. So for vector processing with SVE, another parameter is needed, that is the predicate. It works like a mask. So as you can see in the right diagram, vector registers are logically split into lanes. So the predicate, it indicates which lanes are enabled for the processing. So only the lanes that are enabled will be processed. Okay, this is some basic concepts. And for the operations that are supported by the vector engine, it includes basic load store, math operations, and logic operations, and something else. Here I only listed gather load and scatter store. It is part of load and store. What it means, it supports operating on discrete data addresses. Typically the vector is loaded by a consecutive data from the memory, right? But with gather load, data from discrete addresses can be loaded at the same time. So it will be very useful for some cases, such as one example I will show later in some table lookup example. And how to use SVE? Typically we use vector processing for a loop. And the predicate that we talked earlier, the mask we use for the operation, it enables another feature that we don't need to care for the tail of the loop, because in some loops with fixed vector extension, such as that you process 4 sets of data at each time, and if the whole data size is not a multiple of 4, then you need to take care of the remaining data in a separate section. So here, with the help of predicate, you can just use mask to do that, and there's no need for a tail loop. And here I use some pseudocode to show the whole process. First, we initialize the predicate, and then we start the loop. It includes the typical vector loads of source data and do some manipulations on the data, then store the data back. And after this, we need to update the predicate for next loop. And we also need to test if the loop will continue. Okay, we just talked about the program model of using SVE. And SVE is an architecture feature. It includes addition to the instructions. But programmers, you don't need to use assembly to do that. There's a Arm-C language extension that includes some of the intrinsics, and you can do that. But when programming to use this engine, we need to first check if the hardware has the feature support. First, we need to test the ARM feature SVE. That this feature will be, this macro will be defined at a compilation time if the target platform has this extension support. The compiler will define this. And if you use the C intrinsics, that means programming using C language, then need to also check the header support, the arm.svE.h, if this header is included by the compiler. Okay, that's a requirement of using this feature. And next we go to some experience of integrating this feature into DPDK. I worked on the LPM library. So when we check the LPM library, it already has some vector implementations. Previously, it was the vector implementation was used in lookup, in some lookup API. But this API, it is tailored for 128 vector length. So you can see in the name, there's by 4, because this API looks up the LPM table with IP destination as a key. So for each, here we are talking about IPv4. So for IPv4 destination IP, it is 32-bit. Right, so for 128 vector length, it accommodates 4 IP entries at a time. So this API is defined by purpose for that vector length. So because it is fixed, and it is tailored for fixed vector length. So as we just talked about, it doesn't match the scalability on performance. So then I moved my focus to another API, the LPM lookup bulk. It is a more generic function of LPM table lookup. It accepts several IPs and then look up in the LPM table. So and I will also talk about some performance tuning I done in this work. So you can see in the V1 version, I did it in the VLE, vector length agnostic way. First, we used C intrinsic to generate some predicate to indicate the RPM table entries that we need to load and look up into vector registers. And then after the lookup, and sorry, and then we updated the predicates. So in the first version, I used this intrinsic to check how long should I move for the next iteration. That means how many IP entries are processed by this loop iteration, and then update the predicate. And then after a test of the predicate to check if there's any more work to do in the next loop iteration. Okay, so actually this version of the program didn't give very good performance. So I made some change to it. First, we can see out of the do while loop and inside it, there are similar update to the predicate. So we changed it to the next one. We removed one operation on the predicate. So this gives a little more higher performance. And we also removed the need of check the vector length. Not the vector length, but the entries that are processed in a loop. As you can see, this will be done in each time of the loop, right? So we moved it outside of the loop, so it will be fixed, and no need to do that for each iteration. Okay, and another optimization. Look at the logic. The LPM lookup, it is comprised of looking up in two tables. The table, we can call it table 24 and table 8. Some prefixes, and we can call it a tail. For the most of the IP addresses, they have prefixes less than 24 bits. So only in table 24 will be looked up. So here we add a check to avoid some processing on table 8. As you know, we can write it in this way. It is safe because with some lookups that doesn't need to happen for table 8, the predicates will be 0. So that is safe. But that will also cause some overhead. So we move it to this way. So here, the lesson I learned is that the logic, it will work, but we need to consider the overhead. Okay. And some takeaways from this talk. Did I mention that the compiler can auto-vectorize some program? Yeah, we need to rely on compiler to do the auto vectorization if possible. Yeah, because compiler can do a better job. But if at some time the compiler may not have a whole view of the logic, so it can fail to do the auto vectorization. So that at that places we need to do it manually. But when we program manually, we make sure to follow the vectorness agnostic way. So only in that way we can make sure the program can run well on hardware with different vectorness, and make sure the functionality, scalability, and performance scalability. And some tips for performance tuning. It can be a hotspot for some operations with predicates. That is, the operations are not come for free. So we need to properly use the predicates for better performance. Okay, there are some reference documents on developer site. So you can find some introduction to the feature and some programming examples, and also the ACLE. You can find the C intrinsics for this extension. Okay, that's all for this talk.